Okay, so welcome back, and this is something which is we are talking about the instruction set. In the previous lecture, we did discuss about the move operations, then the arithmetic operations, then some shift operations, right? And I hope you are enjoying this, particularly because you can try this out in the Keel software, and you could also play with it and come up with some combination of instructions which will do something so that you'll enjoy this. Okay, so now the next set is actually this what we discussed last in the previous lecture. So next one basically is on the reverse order instruction. So all this seems to be actually fancy, as I said, unless we find a real use case for this. Okay, so this three things actually I'll just put it over here. So reverse is like reverse byte order in a word. Okay, word is 32 bits and byte is 8 bits. So basically the reverse byte order. Okay, so what is going to happen is, let's say this is the original one. Okay, so byte 3, byte 2, byte 1, byte 0. So rev what is going to do is it will put byte 3 of this particular thing to basically you just exchange the most significant byte and the least significant byte. So this guy will come here, this guy will come here, and then this guy will come here, and this guy will come here. And similarly 16 is like within 16 or within half word you do that exchange. So that means group of 2 bytes you just interchange, and then with half word and then sign extend, that means only the bottom half word will get exchanged. The top one or the most significant half word, what is going to happen is it's like sign extension of the byte 0. Okay, so that's the thing. So byte 0 is in this case is basically this guy, and that sign extension will come. So that's the understanding, and with this let me just quickly show you a demo of this so that it's clear. Okay, so this is the case. Okay, all the things I've written here, it's quite straightforward, so let's do that. Okay, so I'm loading some interesting, same value that, okay, some value here 1 2 3 4 5 6 7 8, so it's easy for you to understand. So here first step is like reverse r1 r0 means all the entire word will get shuffled. And how does it shuffling happens? This byte 12 will become the least significant byte, and 78 will become the most significant what do you call it? Not byte actually, because each, yeah, byte, correct. And then 34 and 56 will get exchanged. So you can see it over here. So r1 is where we are going to store the result, so you can compare. Yeah, 12 became last, 78 became first, and 34 became here, and 56 became here. So it just the bytes are swapped. Okay, so that's happened. Now if I only restrict to 16, that means the within this 12 34 it gets exchanged, and 56 78 it gets exchanged. So you can see it over here. Yeah, 12 34 became 34 12, and 56 78 became 78 56. So that's the idea. And now this is like sign extension, so that means only these guys will get changed like this, and the other one will be like sign extension of the most significant byte. So you can play with it and see. So here for example the basically the 6 is nothing but 0 1 1 0, correct. So it is 0 as the most significant byte, that's why it became all the way 0. Okay, so that's the concept. So I think I made a small verbal mistake here. So the last statement here, so I just changed this, instead of 8 I made it to 7. So it was 7 earlier, so I will make it 8 now. So what is going to happen is 56, so the last statement, only the sign extension statement. So 56 78 will become 78 56, but then 7, the most significant bit is 7 is nothing but 0 1 1 1, right? So 7, the most significant bit is going to be repeated, not 6. I made that mistake. It's after the reversal, whatever is the most significant bit will get extended. So since it is 7 in the previous case, the 7 is nothing but, in terms of binary, it is nothing but 0 1 1 1. So most significant bit is 0, and that is why we saw it as 0. Now let me actually make this as 8. So 8 is nothing but 1 0 0 0. So the most significant bit is 1, and then it becomes sign extension, means FFFF in front, right? So let's see if it is going to happen. Okay, so I will made it happen, and then let's do it. Okay, so all these are done. Yeah, this is the statement, which is, you have a look at r1, so you can see it all FFF, because 8 is the most significant byte or word, most significant nibble, and then the most significant bit is 1, that is why it all became FFF. So that is rev sh command. I hope it's clear and there is no confusion here. Okay, so going back here, so this is what I was talking about. So this byte, the most significant bit, will get extended. So this you will be thinking where it is used, but it is extremely useful in many cases. If you want to exchange the data within a word, you want to exchange the bytes, sometimes you may have to do that. So then in those cases you will find these instructions extremely useful. The next set of instruction is the sign and zero extension. So this as the name suggests, it is just to extend some values. So for example, so we'll take this example rather than going to the explanation, which you could actually refer to the document and learn by yourself, so I won't do that. So let's say the R0 is loaded with this particular value. Okay, now you are doing XX TB R1 R0. So this literally means that the sign extend the byte. Okay, so you have this 8765. Okay, so that particular thing, okay, so byte is basically 65, sorry, so 65 will be untouched, and then whatever is the sign bit of this particular thing, this again 0110, so 0 is the sign bit, that will get extended. So this is self-explainable. This is half word, so that means 8765 will be kept as it is, and the most significant bit of 8, which is 1, which will get extended, that's why it's all FFF. Similarly, unsigned extensions are also possible, which is same as this. So unsigned XTB means the least the byte will be kept and the remaining will be all 0. Half word, TH is half word, that means 8765, the 16 bits will preserve, the remaining will be extended with zeros because it's unsigned. So I don't need to actually show this, I think it's quite straightforward, you can actually try it out. This is the most funny part. Okay, so very interesting aspect, and you will love this because there's a lot of useful applications for this. So push and pop, as the name suggests, it's something like you're pushing something and then you're popping out something. Okay, so the literal explanation is here. So when you say you are pushing, that means you are pushing the content of registers to stack memory, and then popping means you're popping out the content of the stack to the registers. So that's the idea. Okay, so this is the concept. So there is a stack memory and there is a pointer associated with it. So basically from the register you can actually, this is like saving the values in the register when you do before doing some operation. So for that cases this is extremely useful. So if you want to preserve the content of the register before doing something, which is what you're going to do in many examples, so then you have to push it to the stack, and once you do every operation you can take those values back by using pop. Okay, very important point actually is exactly written here. So this is against the convention, because typically when you add data to memory you increment the address of the memory, right? Whenever you add the data to the memory you increment the address of the memory. That's very common, right? That's what we did in our 8-bit microcomputer also. But in the case of stack, since it's something like last in first out sort of approach and it grows down, so what is going to happen is whenever you add a content to stack, the stack pointer is going to get decremented. So that's the interesting aspects, because you're going to start from here. Okay, so let's say, so you fill this position, then you go to the next, but then the address is actually going from high to low. So that's the concept. So keep that always in mind. Whenever you are doing the push operation to stack, that means you are adding memory to the stack, you are going to decrement the address, not increment the address. That is because stack is growing upside down, not the normal way. Okay, and then very important, a stack is like last in first out. That means you add something, let's say you add content of register R0 first, then R1 second, then R3 third. So what is literally going to happen is you first have to remove the last content that is added, I mean last in first out. So basically R3 has to be popped out first, then R2, then R1. So something in that order. So basically what goes first in should be last out, or the reverse. What goes last in should be the first out. Okay, you will understand. I will have tons of examples. So one important aspect, again this is important to understand, the order in which registers listed in the register list does not matter. So what I am saying is, actually let's say I am going to write push R1 to R4 or push R4 to R1, both are same. So it just means that when pushing the multiple registers, it's mentioned here, when pushing the multiple registers, the registers are automatically sorted, okay, and the lowest number registered is stored to the lowest memory address, that is stored last. So that will be the first one which will be popping out. So basically what I mean is this: R6, R7, R8, if we give in this order or this order, both, what is going to happen is first R8 will be stored, then R7 will be stored, then R6 will be stored, so that R6 is the first one which will be coming out. Always remember that, okay. So it's something like this. So first will be R8, then R7, then R6, even if we give in any order, okay. So it doesn't matter. So I have an example. And then where is it used? There is a very interesting application to it. Can you pause the video and think where is it used? Okay, don't worry, I'm sure you won't be able to understand it. So one of the interesting aspect is swap the content of two registers R1 and R2 without using a third register. So many times it's important. So you do this, something like this: push R1 R2, or you can write as a single line push R1 to R2, because that's also the same. So then what is going to happen is the content of R1 and R2 will go to the stack. Okay, so this is going to happen. So push R1, let's go step by step. Push R1, so the content of R1, let's say this is the content of R1, so this goes to the stack. Okay, so the stack pointer was somewhere here, so this is the new address which is free. So that is actually, so stack pointer was storing this address, so the next location is where you will get updated. So R1 will go to this particular location. Now I am going to do push R2, so that means this content, R2 content, will go to the next location. So but remember, this is the address, it's ready to be popped out. If I use a pop command, this is a value which is going to be coming to the register. So what is I am going to do is pop R1, because I want to exchange R1 and R2. So I push the content of register 1 first, then register 2 first, but then the content which is ready to be popped out is the content of register 2. So that content I want to pop it to R1. So that's what I'm going to do, pop R1. So that means the 2 value will come and sit in R1 now, and then if I do pop R2, the 1 which is actually here will come and sit in R1. So without using any other register, I swap the content of R1 and R2. So only 3 commands are needed, which is push R1 to R2, then pop R1, that means the last one which is ready to be popped out. Oh sorry, yeah, I made a mistake, not this one, but push R1 R2 will not work. Why? Because R2 will be stored first and then R1 will be stored, right? So then it really has a problem. So you have to do literally this way: push R1, then push R2, then pop R1, so that R2 will come to R1, and then pop R2 so that R1 will come to R2. Yeah, I think sometimes it's good to make that mistake. So what I'm saying is, like, the command push R1 R2 will not work, because R2 will be stored first and R1 will be stored second, so that R1 will be ready to get. It will work, but then you have to change the order. Okay, so let me actually show you this part quickly, and then we will come back. Okay, so this is the code. I combined all the aspects so that it's easy for you. So I'll explain what is happening here. There's a mistake I made purposefully so that you can correct it. Okay, so let's actually build it, and then of course run it. Let's see. So I'm just going to skip all these because you are well aware of this. Yeah, so R1, R2, R3, R4 I'm just storing by the same number. So 1 is all ones, 2 is all twos, R3 is, so you can see over here also. So R1 to R4 are filled with the values. Now I push R1 to R2. Okay, so what is going to happen is basically, so pushed already R1, R2, R3, R4, and popped R1 to R4. And even if I push R4, R3, R2, R1, doesn't matter, because as I said, the highest one will be stored at the first location, then the next one, then the next one, so that the lowest one is ready to be popped out first. So that's what happened. So there's no change happened. You can see it over here, irrespective of I'm doing this way or this way. Otherwise you have to manually do it one after the other: push R1, push R2, push R3, push R4, but that's very tedious. Right now this is the swapping part. So R1 and R2 I want to swap it out. So let's actually, you can actually see the address also. Okay, so whatever numbers are storing in the address, that those things you're well aware from the first lecture, so please do all those experiments within yourself. But now let's come back to this. R1 and R2 I want to exchange, so I'm going to push R1 first, then push R2 next. Okay, so I did that. Now R2 is the one which is ready to be popped out, so that's why I'm going to pop that content to R1. Okay, so that's why you can already see that is done and this is done. So that means R1 and R2 are actually exchanged. Unfortunately I run that's why. So again you go and change it to 1 2 3 4. Now again I want to change this, but this time I'm going to do push R1 R2 together. Now if you do this R1 R2 together, what is going to happen is first R2 will be pushed, then R1 will be pushed, right? So that's the idea. So then if I pop R1, what is actually ready to be popped out? It is R1 only, so there is no change. You can see it over here. Even if I execute, there is no change here. So how to go about correcting this? Let me go out of the debug because we need to correct. So forget all these, concentrate on only these 4 lines. I want to exchange R1 and R2. Okay, so basically you pushed R1 R2, so that means R2 will be going first, then R1, and R1 is ready to be popped out. So here I should not do pop R1, instead it should go to R2 because I want to exchange it, right? So if I do this, it will work. So you are pushing R2 first, then R1 first, then you popping out R2 to the content which is ready, which is actually R1 in the stack memory, will go to R2, and then R1 will R2 will go to R1. So that's the idea. So let me do this. Play with it if you're not understanding or my speed is too much, because you can always play with it. Okay, so I'll do that. All these things you already saw it. So now let's do this. So you can see I want to exchange these 2 components, so I will do that. So I already did this. Now that last component which is to be, or content of the stack memory which is ready to be popped out, is this guy 1111. So that's why I put it as pop R2. One more line, pop R2. That's it, you exchange it, done. So this is the best way to study, right? Because you will be understanding what is happening in these cases, right? So I hope this part is pretty clear to you. And then yeah, so that's it. So most of the major instructions we have already literally covered. So, okay, so that's the interesting aspect. Now the next one is sort of a branch and compare. So let's do this. So branch is something which is very interesting, which is used in all your for loops, if loops, while loops that you write in C. So when you write such a code in C, you just remember that beneath underlying in assembler, it is getting converted to usage of these commands. So branch, so you have branch to label. Okay, so this is like you can specify branch to some location in your code. Okay, so you remember label is what you are writing on the extreme left hand side, which is like address location. So you can directly branch to that address location if you want. Okay, then you have this is something like branch with links. All explanations please refer actually, because I don't want to go into each and every detail. So you can always go back to the document and then read for yourself. It's very easy to understand, there's no complex thing about it. And then branch indirect, so please understand the differences. What are the differences between these 4? Branch indirect, so branch CC is what we will use most of the time. So these 3 things we very rarely use. This is what we will use, and I have a detailed explanation. So you can actually branch with respect to certain condition. Okay, something like the flag conditions, the flag register, right? Based on those conditions you can do some operations. So that's what I mean by branch conditionally. That's what you do in if and if loops, for example, or for loop, for example, right? Or while loop, for example. Okay, so there are other set of commands which is compare. So compare negative, then compare. So test is like AND operation. So the difference, so basically compare negative is nothing but it is same as add as, but except with that the result is discarded. So whatever is the result in the register, that is discarded. Only the flags are used, because our objective is to do some comparison between 2 variables or 2 registers. Okay, so that's the thing. Only effect of comparison, so just to highlight, is to update the condition flag. No need to set. Okay, so the S bit you don't need to actually do something like add S that you do in add, right? There's nothing like that. It's just you did this. So the flags will be automatically set based on this operation, and based on that you will do some operation. So I think some examples will illustrate it much better than the verbal. So I'll just, so there is no need to use the S bit part, something like add S, or no need to specify the destination register, because I'm discarding the result. All I'm interested in the flag only. Okay, so you may be just wondering what I'm talking, but don't worry, we'll have some examples. So this is what I was talking about. So B B will not stand alone, you have to put some value here. So BEQ if you put, that means branch equal. So that means you do, if the 0 flag is set, you do some operation. Okay, so you do some addition operation or you do some subtraction operation, and then if you do BEQ, that means you are effectively saying that if the 0 flag is set. So 0 flag is typically set when you subtract two values, and if they are exactly equal, that means the 0 flag will be set, right, because the result will be 0. So based on that, so it's something, maybe I will just go to an example rather than showing. So a lot of options actually for conditions. You have equal, you have not equal, you have higher than or same, you have lower than, you have negative, so many options. So you will have to use a branch less than, branch greater than, branch less than or equal to, all these are there. So let's take some example. Okay, so in C, for example, just let's say you have which is greater, -1 or 1. So this is one code that you want to write. Okay, so you have int xy, then x is initialized with -1, y is initialized with 1, then you write something like if x greater than y, you do some operation. So what is the exact replica in assembly? So let's do that. So move R, so basically this initialization you have to do something like this. So move as R1 with this particular value. Okay, so this is basically like the 2's complement, or the representation of -1 in 32-bit, and then 1 is something like this. So then you compare these two. So basically you can use something like R1 and R2, you compare, and the corresponding flags will be set. So if they are actually sort of, when you compare, you can directly use statement like this. So BGT, that means if R1 is greater than R2, then close. Okay, so that's what exactly happening. So something like 1 to 1. Okay, so you can try this out and see for yourself it's working or not. So this is the idea. So you need to have a compare or some operation before, and then you can, based on this, you can actually write your branch operation. So B, the condition here is greater than. So I have another example coming up. Yeah, so this is something like an if loop. So you have if a less than 0, if that is the case, then you do a equal to 0 minus a. If not, you do x equal to x plus 1. So this is something basically irrespective of this, you have to do x equal to x plus 1, right? So that's the case. So you can do it two ways. In fact, two ways I could foresee. You can actually think about it if you want to do it many different ways. So one way is something like move to R1 the a value, whatever you desire, move to R2 the x value. Okay, so variables are set. Now you compare R1 with 0. Okay, so this is basically the operation. So comparing R1 with 0, BGE, that means if basically R1 is greater than 0. Okay, so that means a is greater than 0. Okay, so if a is greater than 0, you need to do this, right? So basically you, if greater than 0, you need to do this. If, because a is greater than 0 means you go to this step, right? So that's what BGE end if. So this is the label for end if. So you do this, that is this operation. But if BGE is not happening, that means R1 is not greater than 0, that means R1 is less than 0. But the BGE means greater than or equal to 0. Okay, so that's why it's confusing. So R1, if it is greater than or equal to 0, you go and doing this operation. If R1 is less than 0, it will go automatically here, right? RSB reverse subtract, R1 is R1 minus 0. That's what exactly this operation is. So this is one way to go about it. Another way is slightly more complicated, which is the initialization remains same. Again, the comparison is also same. So instead of GE, I'm going to use LT. So if it is branch less than, then I have to do this operation. So branch less than, it is then. So that is this. But otherwise, I did a very interesting stuff. What is otherwise? So if it is not less than, it goes to here, but then it is diverting. So branch to some label. So B end if is this, that is this operation. So take some time to digest this. In classroom, I would have actually asked somebody to explain this in your own way, or even derive this in your own way. But here we don't have that luxury. But you can try this out in the Keel Microvision and see for yourself whether it's working or not. So this is the way we write if loops. I hope it's pretty clear. So please go back and understand these, read through that manual thoroughly, and you will be using anyway in the lab experiments, the branch particularly, many times. So that's why I'm not having a lot of examples here, but yeah, we'll take another example. So just to make it very clear, so here I have two things, right? If a equal to 1, if that is true, b is equal to 3, otherwise b is equal to 4. So let's see how it happens. So it's pretty, I mean, you should be able to write it by yourself. So first of all, initialize registers r1 and r2 with a and b, and then you are comparing whether a is equal to 1. So a is nothing but r1 for us, so r1 is equal to 1. Then if not equal to, bn is nothing but not equal to, if it is not equal to, you just need to do this, right? So if it is not equal to, you go to else, which is actually r2 is equal to 4. r2 is nothing but b, so that is equal to 4. But if it is equal to, then you have to do b is equal to 3, that is r2 equal to 3, and then see, you have to put this statement, otherwise what is going to happen is it going to execute this, right? So that's a problem. That is why I am diverting it to end if. I should not execute this if this is satisfied. So basically, if b is equal to 3, I should not go and overwrite b equal to 4. That should not happen. That's why b end if, so it goes to end if, and you write your next instruction here. So this is very easy, very fun to do. So please do this yourself, and that's it. Another example. So let me just go to this. I hope I'm not rushing off, but one advantage with video is like you can pause and then rewind it and hear what I'm saying. Okay, so there's no confusion. So now this one, can you write it? Please pause, don't see what is the result, please pause it, write the assembly language code for this. So this is the flow diagram. So it basically says that int I, okay, so int I in sum equal to 0, then you count for I, basically I is incremented, and then I less than 10 if it is yes, if it is I less than 10, no, I is greater than 10, you come out of the loop. If it is I less than 10, it's like cumulative sum, you are adding one, I mean I, as long as it is less than 10. Okay, so that's the idea. So how does it work? So move r0, r10, all these things you can do. Then you compare r0 with 10, right, because you want to count till 10. So if that is happening, if it is greater than, so if r0 is greater than 10, you end loop. That's what happening, right? If it is greater than 10, you end loop. If it is not, add r1 is equal to r1 r0. So this is the summation, sum equal to sum plus I, and then r0 you just increment by 1. r0 is nothing but our I in this case. So again it goes to this, and then b loop. So it goes again it checks whether it's less than 10. If it is not, it goes again it goes back here. If moment it becomes greater than 10, it comes to end loop. Is not it fun? It is, it should be. You just try to write out all these, and we have tons of such examples in the first lab that you're going to do with Keel, but unfortunately we'll be starting with the other lab first, and then we will go to microprocessor lab later. Okay, so that's it. So then some other examples, so I will not explain this in a lot more detail, but you can actually very easily understand what is happening here. So assume we have 5 values, which are these values here. Okay, so these are the values that you are going to have. Find the highest number and its position. So that's the idea. So find the highest number out of this and put the position in R1. So in this case, for example, you can easily literally say that this is the guy, right? So this guy should come out and the second position should come out in R1. So this is the code I am writing. So you can actually see that there are 5 variables. So there's a variable count, and at the start, let's put the max is equal to 0. And then you loading the address, this particular location in here. So my data location is loaded in the pointer. So you can actually see that we are initializing. So there are ways actually. So this is the way I'm going to introduce you. Instead of putting R0, R1, R2, those are very difficult for us to follow when you write the code. So you can write something like this. So count is nothing but register R0, max is nothing but register R1, pointer is nothing but register R2, next is nothing but register R3, and then it's very easy to actually explain to somebody, right? So you are actually seeing next, okay, and next will be the pointer, so the address is in next, and then you compare max and the content of next, right? So that's what you're going to do. So if that is not the case, then of course you follow the branch if old max is greater than, so max, okay, so b hs higher than and equal to something like that. So you can actually check for what is hs meaning, understand this. So then you go to ctnu. If this is satisfied, you go to ctnu. Okay, so basically if not, you just replace with this, and then okay, so this is self-explanatory. It's something like you go and see each value, and if the value is greater, you store that in the max value, otherwise you go to the next value and so on. So it's like pretty easy to understand this code, it's not difficult. So please play with it and see whether you are able to change these values also, and see if there are any issues with the code and correct that for yourself. Okay, so some lab examples which you will be doing, so I will not be explaining. So one is like factorial of n. So you will have an assembly language program which will take any value of n and find its factorial. Then there is maximum value and its location in a given array, which is very similar to what I explained to you in the previous slide. And there are some other examples where you find the parity of a bit, okay, or a parity bit value based on this conditions. So then of course convert string to an integer. This is very interesting experiment, because the keyboard that you have in your laptop or the desktop attachment, right, they have letters in that, and that all the letters and the numbers will have an ASCII value associated with it. So whenever you press the keyboard, the system understand it by some ASCII number, okay, so it gets converted to some number. So that's the one you are going to do in this experiment, the last experiment in the lab. Okay, so with that, yeah, the all lecture on the instruction set is over. It's not very complicated. There are a lot of instructions, in fact 56 instructions that is there. Always refer to these documents that I was talking about, these two documents. The instructions are explained in full detail here. Okay, so you can see it over here, all the instructions are explained. If you go to the respective page, full details with some examples are also explained. Many of these instructions I didn't explain in the videos. The purpose is like it will be terribly boring, and I only introduced some of them which is very interesting to you. Okay, but please have these documents ready with you, understand these instructions, don't by heart it, and use it as and when it's needed, particularly for the lab experiments. So with that, we are complete with the lecture on instructions. Okay, so I highly encourage you to play in Keel with all these instructions, understand all the instructions well before you come to the lab, so that it will be easier in the lab. Okay, so that sort of concludes this week. I'm not going to load you with lot of lectures, because this week we are starting the lab, and you will be busy with that. So we'll just stop, and that's it from my side. Thank you, and see you in the next week.